let's talk more about the zero knowledge. So what we've done so far is we've just set up everything that has already been written, and we've walked through a little bit of how to inject the zero knowledge that we've already created into our application. But what zero knowledge do we have? And I would encourage you to check out the Circom 2 documentation. It is for sure lacking. There's a lot to be desired, but it's the best we have, and it's still, again, the software under the hood is amazing, so it's still kind of the Bible. And there is the Circom language. This is probably the most important part right here. And this grouping of information that was put together has been the most valuable for me so far, and I think you'll probably find the same. So there are concepts essentially of templates and components, which are very much interchangeable for the concept of contracts. The arithmetic encoding that has to occur to do these computations requires you to write code in very weird ways. So when I'm drawing these analogies between smart contracts and circuits, it's in the way that Solidity has its own weird components to it when you're coming from writing like Java or JavaScript. But there are a lot of differences, so again, be wary of that. But a template is also very much like a contract, and you can write sub-templates, and templates have a concept of signals. And I am not going to go super in-depth on all of this different, like there are also functions, and those don't work with signals, they just work with numbers. And there's a lot that goes into the concept of signals. That it's a very deep topic that requires a lot of understanding to be truly proficient with, but you can also for sure just kind of sling stuff together and it'll kind of accidentally get working if you play with it enough. So let's start with board, and this is the first zero knowledge proof that we do in either new game or join game. And the public input is ships. And this is one example of what exactly the data of ships will look like. And in a little bit, we'll show you what it looks like on the UI board when you place it. But when you do, there are three numbers that are used to coordinate: an X position, a Y position, and a Z position. X and Y can be between 0 and 9, and Y can be either 0 or 1. And based on where you try to put it, as well as whether it's 0, which represents horizontal, or 1, which represents vertical, we need to check whether 5, 4, 3, 3, 2 in units, spaces on the graph, long ships, will either intersect with each other or go off the board. And that is what this proof will do. So going back, we hardcode these lengths, and we have as well a hash, which I'm going to skip ahead and talk about the hash really quickly because it's surprisingly easier than conditional computing in zero knowledge. So we have a MIMC sponge, and I believe using something like Poseidon, which is an extension of MIMC, would be superior to MIMC sponge, but compared to using something like SHA-256, it's still way better. We used Plonk, we used Gras16, so we used what we could get working from the Circumlib library, and we'll actually go look at that right now. So you can see we can import it actually from NPM. This you can import from NPM. You can import Circumlib circumlib.js, circum tester, all of those things are fine to import from NPM. The only thing you cannot import from NPM is the actual Circom language SDK. That has to be imported and built in Rust. So here we have all our circuits in NPM, and you can also view this all in GitHub. But a lot of this is going to make absolutely no sense to you the first time through, and this video is not going to be too much help. There needs to be a lot more that goes into documenting all of this. If you are not coming from an academic background, it is a slog for sure, but it is doable if you stick through it, and it is incredibly rewarding. But we do use, what we'll use in our rollup is EDDSA MIMC most likely, or we may actually swap to Poseidon. But what we use right now for MIMC is the MIMC sponge. And I don't get any of this. I don't think anyone does, except people who have written very lengthy mathematical papers. So don't worry about it. Don't worry about it. Use the built, tested, standard primitive and be on your way. That's what circumlib is about. That's what Open Zeppelin contracts is about. But going back, we define one output, 220 rounds of hashing, which is default. Just set this as 220. If you need more than one, you can set it to more than one, but we generally don't need more than one. There are plenty of reasons why you could, but and then 15, so we're doing a multi-hash, which takes the 15 inputs shown here, the 15 inputs given here, and passes them in. And this notation is the process of signal constraint generation, and somewhat out of bounds of what I can really speak to today. And there are points where your computations, your code will become too complex to put into arithmetic terms. So there are very important steps you have to take in order to ensure what you will very quickly run into can be non-quadratic constraints from your code, which is very annoying, but navigable for sure. So going into the first range check, we'll start with that. One other thing is we can pass into templates a value n, and what we do is we use this to pass in how long the ship is, and then if we go back, we have this here. So each ship we create, we do 5, 4, 3, 3, 2 in our for loop, and this enforces the constraints. So we don't need it in board, but you can see kind of how parameters and templates work that way. So we have the ship range proof, and we can first see that there is less than, and this is from the circumlib comparators library, and you're going to want to take a look at all of these when you're trying to make evaluations between two numbers. It's annoying that it's this low level, but with all of the magic happening under the hood, you have to be able to be a little flexible, and all things considered, this really isn't that hard. But it will ensure proper constraint generation to do all this. And what we're doing is essentially guaranteeing that if this is vertical, that it is constrained correctly, and if it's horizontal, it is constrained correctly. And this now gets into signal muxing, and I struggled with signal muxing for a while in my 4 months of research before ETH Denver, 3.5, I guess. What I couldn't understand was that even though we were encoding all of these as signals in circuits, why multiplexing signals, which was a common thing for electrical engineers, was now making its way into this domain. I still couldn't understand why if there were if statements in Circom, I couldn't just use those. And the thing is, you just can't. If statements really don't work the way you want them to in Circom, what you need to do essentially is you can't branch your computation. You have to, if you have two possibilities, in our case Z, your ship is either pointing horizontally or vertically. You can't compute either one in Circom, the proving language. You need to compute both of them. And even if the one you don't care about would be producing a wrong value, you just discard it after the computation, and the multiplexer lets you choose the correct one. So the way that works is we do our computation and get is okay for X. And then we do our computation, just checking if it's in the bounds of 10. Is okay 0, is okay 1. And then what we do here is make sure that Z is either 0 or 1. We make sure Z is horizontal or Z is vertical, because we don't use Z for these computations. In this, we assume Z is 0. In this, we assume Z is 1. And then we use the mux, the multiplexer, to choose which value we want to use, which is okay value we actually care about from Z. If it's 0, we care about X. If it's 1, we care about Y. And then we pass in to the selector Z, and that whatever comes out here is the one we actually care about. So all of this is one massive switch case. It doesn't look like it, but it is. I'm sure people will make advancements in higher level languages that abstract away a lot of this, but once you understand how the switch case kind of works, it's really not that bad. It's just that, again, the documentation can be confusing for someone who doesn't come from a mathematical or electrical engineering background. But hopefully this helps clear that up, and we'll go into some more examples in a minute when we get to placing ship and hitting ship. So we check everything's in range, and then we place the ships. So what we do with the collision check, I think is a little smart, but it's what you have to do, and it's something that hopefully you will be able to replicate as you start your journey building with Circom. But in order to have a state that I am constantly both checking and adding to, it was a little difficult. So essentially what we have is a 10 by 10 board that is a bitmap. It's zeros or ones, and it tracks whether or not a ship has been placed there. And as we get into the place ship function, how place ship works is it takes an input state, which is a numerical representation of a bitmap, a ship that we're going to add to our bitmap, and the output state of our board. And on the very first pass in this, it's going to start as 0, which is going to map to a, mentally how we want to think about it is a 10 by 10 board of zeros and ones. This board right now on the first go has no ships placed on it, but we want to place our ships down on it and track as we place them whether or not they collide with our previous placements. It's confusing for sure, but we'll try to walk you through it so that you can replicate it in your own code base when you want to do something similar. So essentially, again, we're placing a ship in, and we want to see if there's a collision if Z was 0 and a collision if Z was 1. And we use the collision mux to choose it, and then the board mux to do the state passing out, and we'll get to that in a second. And then 2 bits is what allows us to turn our board in to our bitmap. So we do that, and then we store board V and board H, which are two temporary ephemeral representations of the boards that we're going to be working with, because we need to compute it on both the horizontal and vertical conditions for our ship. So what we do here is maybe not the smartest way to do it, but it's just if the ship's 5, it's 5 ones. If it's 4, it's 4 ones. 3, it's 3 ones too. So we could have gone about this a little smarter, but it works for sure. We just want a bitmap with a bunch of ones. And the idea is that we expect it to only be ones on the board. If there's no placement, it's 0. If we've placed our ship down, there's ones. But if we collide, there's going to be 2s. And that's what we're expecting, a bunch of ones. So really it could just be 1. We don't even need this, but a lot of coffee and a lot of sleepless nights were spent building this in 5 days for ETH Denver, so give it some slack and make your own fixes if you want. But we do our checks horizontally and vertically, basically by adding the values on the board, and then we take the cell value and we see right here we can check if a value is binary, and this will output into V collision, which is either 5, 4, 3, 3, or 2, depending on what pass it is. It lists the collisions. Either it was 0 or 1, in which case there was no collision, or it was, and the value will be 1. Or there was a collision, the value is 2, and V collisions dot in at index I will be 0 because it did not pass. So then we use the multiplexer to choose which of these horizontal or vertical constraints we want to use. So if it fails this right here, then it means that it did not pass the placement constraint. So from here, again, because we have to multiplex to choose our cases, we have to do this with state as well as constraints. So we convert both of our board representations that we've now placed our ships on into a numerical representation so that we can pass it into the multiplexer and choose, again with Z, like we did here, which state we want to continue to work with. So that goes out, and then we take the output. We don't actually use it directly as a signal necessarily here. We pass it as a variable so that we can work with it without constraints to a degree. But we just take that numerical representation of the state which we've chosen, because again we multiplexed to choose the board state that we are working with, and we loop and pass it back in, and it goes right here for the next computation. So we can iteratively add to this board state and perform this conditional computation on it, but only with some caveats. So we've done the board, and this shows what happens when we join a game or do a new game. But we still now have the main driver of our battleship game. All we've done is enable us to prove that we have a hash of a valid board configuration. And we only need to do that proof once for each person. We then store it, as we mentioned, on chain, and we trust it. It's okay now. So what we want to do is next we want to have a proof that a shot hits or misses a certain board configuration. And there's no way for someone to prove that their opponent had a hit or miss, but they can prove their own is a hit or miss. So that goes back to that reactive idea of proving. But the inputs it takes are the ships, the hash, the shot, and the hit. And this is actually, I think, something I might have skimmed over in board, but you can see that only these ones are included here. And that is because we don't want this part of the computation to be included. This is private, hidden information that when we go to verify it, shouldn't be used on chain or anywhere else public. So there's this fourth value, which again is the hidden private positions of the ships, because we need to know that to do the proof. But it's not public. You don't have to reveal that, and that's where that hidden information comes from again. So you can see our friends MIMC, Sponge, and comparators are going to make a comeback, but we also have gates now. And what we're using are a bunch of OR gates. So the first thing we do is a very simple range check, because there's no concept of horizontal, vertical extension out for a certain length. All we have to do, this 4, you saw less than 4, that 4 is because 10 is a 4-bit number. It can be represented in 4 bits. So if your number was 5 bits, you do less than 5. If your number was 2 bits, you do 2. If it was 256, you do 256, but that's where this number comes in. But we check that x is less than 10 and y is less than 10, and if both of these values are 1, they'll multiply together to be 1, which is true. Then we've got a hash integrity check, which is literally the exact same code used in this. We basically want to check again that the hash provided before is the hash provided now, and that allows us to do all this computation trustlessly without any sort of other knowledge that we need. And now we get into the hitscan, and this is kind of similar to placeship, but a lot easier. But we'll get into it. There's no passing of state in between this loop. So essentially all we have to do is pass in the ship, pass in the XY coordinate that we're checking if it intersects with, and outputting whether it hits or not. So we compute horizontally whether it hits, vertically whether it hits. Essentially what we do is we want H hit or V hit to be 0 if there is no hit that happens on the scan, and 1 if there is. So it starts as 0, and then we do a check that sees if either of these intersect on each condition, X or Y is extending. And if both of them are in one of these cases, then we can multiply it by 1 and it'll increment. But otherwise, if they both are not, if it's not an XY hit, it'll be 0. So it'll just be 1 times 0 plus 1 times 0 plus 1 times 0 plus 1 times 0 over and over, and it will be 0 by the end of the computation. But if there's ever a 1 in there, there will be a 1. If you try to do, you'll run into some quadratic constraint issues. I think because we still here and way up here constrain it, it's okay. But using something like assert would definitely not be okay, and you have to be careful for sure that when you use this, you later constrain it with some sort of value like that. But since we're just doing a computation and there's not too much that goes into it, it's okay to do this, I think. So we produce basically a 5, 4, 3, 3, 2, the different ships. We produce a list of whether or not it hit for each of those ships. And we use, because there are 5 different values, we use a string of ORs together, basically, from our OR gate. Because it's, if any of one of these values is ever 1, then we know a hit occurred somewhere. So what we do is if 0 or 0 or 1 or 0 or 0, it's going to return a 1. So again, we just string these all together to get either a singular 0 or 1 value as to whether or not there was a hit. And then for the main actual function that we care about is we assert that the publicly stated hit value is what we computed. And if it is, it is. And if it isn't, the circuit will fail. It'll cryptographically fail to verify. And that's the entirety of our Circom. Again, we've kind of talked about really how this all fits together. Let's start testing it a little bit. So we split this video into multiple parts, which is why the continuity is probably a little weird, but there should be 3 videos dropping at once, so yeah. Go check out our Discord. That's going to be the best place for you to ask questions about this or any other builds that you want help with, or just any discussion around zero knowledge. But you can also subscribe to us here or follow us on Twitter as we release more Circom zero knowledge content in the future. So check the description. Links to all the socials are there, as well as links to all of the content referenced in this video. So yeah, see you in the next one.